So we've now found that these complex exponentials are the eigenvectors of a Hermitian operator. We get to build an orthogonal basis out of them. Now we're going to make this an orthonormal basis. We're going to talk about how this looks in practice and how to normalize them. So our vector space is all built on a line that goes from A to B. Our functions start at 0 and end at 0 on this line. Or if we're going to extend this out, we say that the function is periodic on this part of the number line. So our basis also needs to be periodic on this part of the number line. So if I have e to the I k a, that better be equal to e to the I k b on the other end. Now, the nice thing about the exponentials is that you can always take a 2 pi lap around and come back to where you started. So I will still get the same results if I put in many 2 pi's here, positive or negative. And that comes back to e to the I k b. So if I want to isolate k, what I'm going to get is 2 pi over b minus a times n. So what we have here is a discrete k. We can count off these k's by integers. They make a list. So if I want to write my function as a sum of eigenvectors with coordinates on them, just like how for a normal vector, this would be some coordinate times unit vector. Now, my function is going to be summing over all integers, some coefficient times my eigenvector, where we count through the k's like this. And we could also write this with Dirac notation if we wanted, where f is a vector, and we sum over all modes. And we treat this as a vector that we labeled by its eigenvalue. We label it by which k we're on. And we know that I'm talking about the complex exponentials here. But this isn't normalized yet. So let me do that. If I want to normalize these, that means that if I dot product a kn with itself, I'm going to get 1. But now I define my dot product. This is an integral, and I can just chug through that. So I'm going to integrate from a to b over x of e to the I kx, that's starred, integrated with e to the I kx. Oh, I should also add, these have coefficients out. We need some sort of normalization constant. We want these to be equal to 1, but they're not there yet. So I'm going to have a normalization constant alpha, e to the I kx, all of that gets starred, with the same thing unstarred. So my alphas just pull out, and inside I have e to the negative I kx plus I kx. Multiply these, add the exponents. That is 0. And e to the 0 is 1. So what I get is the length of my interval times the alpha squared. So to normalize this, I need alpha to be 1 over root b minus a. Now I've got my orthonormal basis. However, this is only for that set of periodic functions. We've got a normalization constant, and they all look like complex exponentials, where we count through the kns like this. So we've talked about how to do this on a given line. I want to start extending this out, where we take the limit as a goes to negative infinity and b goes to positive infinity. We still need this function to be 0 on the ends, and for that matter, it needs to go to 0 fast enough so that we can integrate it and get a finite number. We don't need to sweat the details right now. Just know that this needs to decay out properly, and our functions are going to look something like this now. So before, my kns looked like something I counted through discretely, but as my denominator goes towards infinity, the steps I take as I count through the integers become smaller and smaller and smaller and smaller. We can have longer and longer wavelengths and finer changes between our k's. So as we take that limit, k is going to become continuous. And now that we have a continuous index, we can't sum over it any longer. These sums only work when you can count things off. If we have a continuous space, that sum turns into an integral. So before, where you could write a function as a sum, even an infinite sum, now this is going to become representing a function as an integral from negative infinity to positive infinity, integrating over all the k's, not summing over them, where we have e to the I kx, and then some coefficient right here that's now a function of k. This is getting towards Fourier transforms. We're going to talk later on what exactly that function of k is inside the integral. Where now my list of coefficients that I can list over n has become a function of the k, of the continuous k. Before, when I took an inner product of different k modes, and I got a Kronecker delta, where it's going to be 1 if they're the same and 0 otherwise. Now, if I've got a 1 inside and I'm integrating over that 1, I get infinity, and that's no good. If I'm summing over this, I'm just going to get the 1, and that's fine. But I need something that gives me 1 at the end after an integral. And that's going to be a Dirac delta function. So this is going to have to evolve so that as I take my inner product over the continuous versions, that needs to give me something like Kronecker delta of k minus k prime that only fires when those are the same. But this means our normalization is going to get different. And so there are some subtleties here that come out where all these 2 pi's start appearing about how we count the k's versus how we count the n's. I'm not going to get into the details on that, but the takeaway is that when we go from our eigenfunctions looking like this, now in the continuous version, the normalization is going to be different. And we're going to have a 1 over root 2 pi out front instead. As for where that came from, just trust me on that for now. This is the high-level takeaway about how you want to think about these things. So I know that you've seen Fourier series and Fourier transforms before, but I want you to look at them now not as a giant table of integrals or a big integral machine you have to feed things through, but as linear algebra techniques.